looking at a table for the f of x function, restricting our attention to x values greater than or equal to 0, we get the square. F of x is a squaring function. So square 0, we get 0. Square 1, we get 1. We square 2 and 3 respectively, we get 4 and 9. Now, we can put x values into the g of x and do square roots. Okay, if x is 0, well, the square root of 0 is 0. If x is 1, the square root of 1 is 1. Now, we might be tempted to put down 2 for x here. I'm not that tempted, because I don't know what the square root of 2 is. I can't write down the exact value of the square root of 2 except to just write down square root of 2. Now I know approximately what it is, and that's actually good enough to give me a pretty good approximation to the graph, but I don't want to do that. I want to use values of x for which I can get integer values of the square root. So I'm going to use 4. Of course, I chose 4 because I can take the square root. It's the next number I can take the square root of with confidence. Okay? And then I can do 9, and I get this. Now, if I look at these two tables, what do I see? What do you see about the pattern of these two tables? Well, the pattern is simply that the columns have been reversed. Okay? The 0, 1, 2, 3 column is now the second column of the g of x function. The second column of the f of x function is now the first column of the g of x function. What does this do to the graph? Excuse me. I've been fighting that sneeze. Okay, well, if we look at the graph, we have the familiar graph. The f of x graph is going to look something like this. In the g of x graph, well, it's going to go through excuse me again. Probably do that a couple more times. Nothing I can do about it. The g of x graph is going to go through the same 2 points, but then it's going to go through the point 4 too. So we've got to come out here all the way out to 4 units before we can come up to a value of 2. And then we've got to go even further. We've got to go all the way out to 9, which is off of the board, so I'm not going to attempt to draw it. But our graph then looks like this. Now this graph, excuse me, never really levels off, because no matter how big you want to make g of x, you can. If I want g of x to be 10 billion, then all I have to do is write down in this line of this column of the table the square of 10 billion, which I think would be 100 quadrillion, 100 quintillion, 100 sextillion. Wait a minute, 10 to the 10th, 10 to the 20th, it's up there. So, what we get on these two graphs is a situation where every point here is associated with a point here on the graph. These points are associated with each other. This point is associated with a point way out there somewhere. And in the middle here, we have the line y equals x. And each of these points reflects to a point in this graph. Now, if I'd done this accurately and drawn the graph accurately, the angle here would have been a right angle. Should have been 90 degrees, but I didn't draw the graph very accurately. If you draw the graph very accurately, these points will be equidistant from this line, and the line connecting them would be a right angle. So we see the property of graphs of inverse functions in that they're reflections across the y equals x line, the line that makes a 90-degree or 45-degree angle with both axes. I didn't have very consistent axes here, so my picture isn't showing that very well. Okay, and I should mention, these are inverse functions.